Okay, so in this example, we have a farmer who, from experience, knows the average heights of apple trees is 2.7 meters with the standard deviation of 0.7. And so at this point, we know this is the standard deviation of the population. Because we know the standard deviation of the population, we are in the z distribution, or the normal distribution. It's all going to be z. If this was an estimate, then it would be t, but we are going to be doing z. He buys a new apple orchard and wants to test whether the average height of apple trees is different. Okay, he's not concerned if they're bigger than or less than, he just wants to know if they're not the same. He assumes the standard deviation is still this fact. State the hypothesis. Well, if that's the case, the null hypothesis is going to be that it equals 0.2 or 2.7. And the alternative hypothesis is that this average height does not equal 2.7 because it's a difference. So this is going to be a two-tailed scenario, so it's not equal to. The farmer then comes along and he measures the height of 45 trees. So I know that n is 45 and finds their average. Find the critical region for a test at the 10% level of significance. So we have to consider that we have a normal curve here. And this normal curve is not the normal curve of the population. This is going to be the normal curve of groups of 45 apple trees. So imagine if I went out and found a group of apple trees, I got 45 and I made a point, and another 45 I made a point, another 45, another 45. If I did this an infinite amount of times, getting groups of 45 apple trees, I would get this normal curve. We believe the mean is 2.7, and the standard deviation of this is going to be 0.7 divided by the root of 45, which is what the central limit theorem says. So this x bar is a normal curve of all different x averages, where the mean will still be the same, 2.7, but the standard deviation is going to be 0.7 over the square root of 45, and I have to write it as the variance. And so I want to find the critical region at 10%. Well, because it's not equal to, it's a two-tailed test, and this is perfectly symmetrical, even though my diagram is not very good, where this is 5% and this is also 5%. And so I'm looking for this value k, k1, and we'll call it k2. And so I'm actually going to try and find the probability that x bar is less than k. It has to be 0.05, and this is k1. To do it, I'm going to go, if I have the area and I want to find the value, I go to my normal, inverse normal, which I know the area is 0.05. The mean is easy 2.7, but the standard deviation is the one you have to be careful of, divided by the root of 45. And that gives me that K1 is equal to 2.53 meters. This is in meters. And when I do the probability that K bar is bigger, or X bar is bigger than K2, has to be 0.05. K2, I go back to here, and I do my inverse normal again, because I always have to go from the right-hand side. This is going to be 0.95. Same values for the rest, and here I get 2.87. So my critical region is anything outside here and here. So if K is, how do I write that? So I want the X critical region. So if the X bar is less than 2.53 or K bar is bigger than 2.87, this is the critical region. Okay, and then finally C part says if the average height of the trees is 2.3. And before I go to C part, one thing I want you to recognize is in B part, I did not use the sample. This can all be done before any statistics are done, knowing this. All you need is a sample size. So now I know that 2.3 was my mean. I want to know what to do. So I'm going to do a z-test. I'm going to do it two ways. One, I could do a z-test with my calculator, And I could just go tests, a z-test, and I have statistics. I have, this was, mu is 2.7. The mean, I know, is 0.7 divided by the square root of 45. X bar in this case was 2.3, and n is 45. Here, this is the mean of the population, or the standard deviation of the population. I don't, in my test, I don't divide by the root of 45 because I put n in, it knows to do that already. And then I'm going to not equal to, and I'm going to calculate it. And I can see, so what it's saying is here's my normal curve, here's the 2.7, and the 2.3 is so far over here, the p-value is approximately 0. And so the conclusion, we will, as the p-value is approximately 0, we reject h naught and say the trees are not 2.7 meters tall. Okay, I did say I was going to do it two ways. The other way I'm going to do it is if we recognize that here's my 2.7 and 2.3 is here, this value here is my p-value and its mirror image because it is a two-tailed test because it's not equal to. So to find that, I'm going to go to normal, CDF. My lower limit is negative infinity. My upper limit is going to be 2.3. My mu is 2.7. But here, I'm not putting n in, so I have to take care of the n myself. It's 2.7 divided by the square root of 45. So that's this area here is 6.32 times 10 to the minus 5. But the p-value is going to be times 2. So times 2. And I get 1.265 times 10 to the negative 4, which will be the same value as up here. And if I redo that test quickly, just look for the values, you'll see that it is the same p-value that was here. And so there's two ways to do it. You have to keep track of what your standard deviation is and which method you're using to put the correct one in the calculator.